Hello, hope you are doing great. Welcome to the Thermodynamics course. This is the first of 12 lectures, the 12 regular lectures for the Thermodynamics course. And on the PowerPoint, we'll look at the course goal and also look at the different topics that we're going to cover over the course of the semester. Our course goal is to understand the thermodynamic properties of the atmosphere and apply that knowledge to weather analysis and forecasting. So in the first half of the class, we're going to look at a lot of thermodynamic theory, and then in the second half of the course, we're going to be looking at the skew-T log P diagram and assessing thermodynamic properties such as instability, moisture, and wind profile. The lectures sequence that we'll be going through today will have an introduction. Lecture 2 will be the equation of state and energy. Lecture 3, principles of thermodynamics. Lecture 4, we'll be looking at water vapor. Lecture 5, we'll be looking at stability and instability. Lecture 6 is when we'll start to look at the skew-T log P diagram. And then in lecture number 7, we'll solve thermodynamic variables using the skew-T log P. Lecture 8 will continue with the skew-T log P. Lecture 9 will look at a wind profile of the troposphere, vertical wind shear, and the hodograph. Lecture 10 will look at advanced thermodynamic index values. Lecture 11 will use the skew-T to forecast severe weather and winter precipitation. And then finally, Lecture 12, nowcasting of the thermodynamic environment. Today we'll start Lecture 1, our introduction. And we'll start by discussing the gases of the atmosphere. The atmosphere is composed of many gases. A couple of these gases, however, nitrogen and oxygen, are much more abundant than the others. Water vapor, although it does not have a large abundance in the troposphere and atmosphere, it's one of the most important gases since it produces the precipitation and water vapor in the atmosphere. Each gas is composed of molecules that are chemically alike. We'll go to the overhead camera and look at the composition of the air in the troposphere. And what I have here is the three most abundant gases. We have nitrogen, oxygen, and argon. And I have here the percent by volume and the percent by mass. The percent by volume is what is usually referenced in many sources, where nitrogen takes up the bulk of the air in the atmosphere with 78%, oxygen with 21%, and argon is about 1%. And each of these gases has a distinct molecular weight. Nitrogen and oxygen in the atmosphere, they'll combine together. Two nitrogen atoms will combine together, two oxygen atoms will combine together to produce N2 and O2. The molecular weight of nitrogen is 28, and oxygen is a little bit greater than that at 32, and argon is at 40. Some other significant trace gases in the atmosphere are neon, helium, krypton, hydrogen, xenon. And some variable gases that are very important. One is the water vapor, which ranges from a trace to near 4% in any given sample of the atmosphere. If it's very warm, humid air, it's closer to 3-4%. If it's very, very dry, cold air, then it may only be a trace. Carbon dioxide is an important gas, although it has a very small quantity in the atmosphere. It's a very strong greenhouse gas. And then ozone is also another very important gas. On the PowerPoint, we'll look at matter. Matter is defined as anything that has mass and occupies space. And there's several different terms that we're going to look at here that are used to describe matter. And those terms that we're going to look at are an element, an atom, compound, molecule, and a particle. And on the overhead, we'll look at the definitions of these. I have 5 definitions here, and what we're going to do is we're going to figure out which term goes with what definition. Number 1 here is the smallest unit of any element in which the element retains the chemical properties that it has. And the answer to that one is the atom. So the atom is the smallest unit of an element in which the element retains the chemical properties that it has. Number 2 says the smallest unit of 2 or more atoms in which the atoms retain the chemical properties that they have. And the answer to that one is a molecule. So again, that's the smallest unit of 2 or more atoms in which the atoms retain the chemical properties that they have. An example of a molecule is water, which is H2O, which is found by combining 2 parts of hydrogen. And hydrogen, just like O2 and N2, it has 2 hydrogens bounded together in its natural form. And that is added to oxygen O2 to yield 2 water molecules. All right, number 3 says this is composed of atoms that are chemically alike, and the atoms cannot be broken down further. The answer to that one is the element. There are several different elements that have been found, and we'll take a look at the periodic table here. In chemistry, this is an extremely important table. It has all the elements, and some of these we are familiar with and we deal with on a day-to-day basis in the atmosphere, and then some of these are not as important. The important ones here, there's oxygen and there's nitrogen. Argon is a noble gas, so it's not very reactive. Other noble gases are helium and neon too. They're not very reactive either. And then when you have certain of these elements that combine together, that produces a molecule, such as ozone or CO2, carbon dioxide. That's another example of a molecule. Our third definition was an element. So our fourth is asked, these are the building blocks of atoms, such as electrons, protons, and neutrons. And the answer to that one is a particle. And then the last sentence reads, this is formed by combining 2 or more different elements. You have 2 or more different elements together, that is a compound. So if you have several water molecules, those were in hydrogen and oxygen were combined together, that produces the compound of water, H2O. But if you just took one individual water molecule, then that's where the term molecule comes in, because it's just one. You've broken it down to the smallest number, which is one single molecule. Next, on the PowerPoint, we'll look at definition of solid, liquid, and gas. A solid retains its shape, is non-flowing, it's difficult to compress, and it has a high density. Whereas a liquid is going to flow. It takes the shape of the container that you pour it in, such as you pour a glass of water. The liquid is going to take the shape of that glass that it's poured into. And the liquid just as a solid, is fairly difficult to compress. It can be compressed a little bit, but not significantly. And then the gas. The gas also takes the shape of the container that it's put in. The gas is going to flow. So both liquid and gases are fluid when they're moving. One big difference between a liquid and a gas is that a gas is very easy to compress. And a gas has a very low density. So that's one reason why a gas is very easy to compress, because it has a very low density. So it's fairly easy to move those molecules closer together. Next, we're going to look at several important definitions. And we'll start with position. A position is a location in space, such as using longitude and latitudinal lines to describe where a location is. So you have to have some type of coordinate system, and the position will be a point on that coordinate system. Displacement is the distance an object moves from one position to another. Speed is the magnitude an object is moving, and velocity is the change in, the velocity is the same as the speed, but you're also given the direction that it's moving from. So if the information just said 10 meters per second, that would be speed. But if it was 10 meters per second from the east, then that would be velocity. Acceleration is a change in velocity per unit time. And then our last definition here, time, can be fairly easy or difficult to define. It takes a lot of thought. What exactly is time? Here's two ways of describing it. It's an interval of movement toward the future, and that one also needs some type of reference system, and the reference system that's used most often is seconds, and through putting a number of seconds together, we produce other units such as minutes and hours and days and so on. Another way of describing time is the progression of events. Since time is always moving towards the future, there's going to be a progression of events leading from the past towards the future. On the overhead, we'll look at these definitions. We have 6 sentences here, and we're going to define what each of these is. The first one states, the car is moving at 90 kilometers per hour. And our choices to pick from here at the top are position, displacement, speed, velocity, acceleration, and time. So the car is moving 90 kilometers per hour. So we have speed here, but no direction. So this one is speed. 2, the wind is from the north at 15 miles per hour, given directional information there. So this one is velocity. 3, the city is located at 35 degrees north and 100 degrees west. So we're referencing a coordinate system and a point on that coordinate system. So that is a position. 4, the car is traveling from one city to another and drove 350 miles. So that 350 miles is the displacement. And 5, it took 35 minutes for the thunderstorm to develop. Only time information is given, so that one is time. And the last one, 1 minute ago, a rocket was moving 200 meters per second. It's now moving 400 meters per second. So the speed of that rocket is changing over time. That is an acceleration. Next, we'll look at vectors. Vectors represent the magnitude and direction. Or the magnitude is the number and the units with that vector. And the length of the vector is proportional to the magnitude. So the longer the vector is, then the greater the magnitude is. Think of magnitude as like speed. If it was 10 meters per second, then it's a 10 meter per second magnitude. And if the vector was twice as long, then the speed would be twice as great. Direction is progression in space relative to a coordinate system. On the overhead, we'll look at an example of some vectors. Vectors are commonly displayed on the forecast models. When you're looking at the forecast models at different levels in the troposphere, you'll often notice that there's little arrows all over the image. And those arrows are giving you information on the horizontal wind, or the wind that's parallel to the Earth's surface, and it gives you an idea of the magnitude and direction of that wind. The coordinate system that we use is up is north, down south, and then east and west. So once we have that coordinate system, when the vector is drawn, we can determine what the wind direction is. In meteorology, it's the direction the wind is coming from. So these two wind vectors here would be described as a north wind, since the wind is coming from the north. And notice that this vector here is twice as long as this vector here, and one vector has a 10 and the other one has a 20 next to it. We'll give it some units. Let's call it knots. So the vector with the 20 knot wind is twice as long as this other vector, to represent that the wind speed is twice as great as it is with that vector. So two examples here. We have this vector, it's coming out of the southeast, so this would be a southeast wind. The wind's coming from the southeast. And this vector here is about twice as long as that one is, so we'll call this 40 knots. This vector here is coming out of the southwest, and it has about the same length as that vector does. So it's 20 knots. Next, we'll look at some basic units that we'll be using in this course. We'll mainly be using metric system, and when the units are not in the metric system, you'll usually have to convert them over to the metric system in order to get the answer. The basic units, we have distance, which is in meters, time in seconds, mass in kilograms, speed is meters per second, and acceleration is meters per second squared. Some other units, area is meters squared, volume, meters cubed. Force is called a Newton, and that's mass times acceleration. The pressure, which we're going to deal with significantly in this course. Pressure is the force divided by area, and a unit of pressure in the metric system is called a Pascal. Work is force times distance, and a unit of that is a joule. Power is work per unit time, and that is a watt. Two more. Density, which we'll be dealing with later in this lecture, is mass per unit volume. And when temperature is used in the equations, it's usually going to have to be converted into kelvins, but sometimes Celsius will work also. And on the overhead, we'll take a look at these units written out, because the way they're written out on a computer can look different than how they're written out by hand. So we start with speed, which is meters per second. That can be written as a meter divided by second, or meter times second to the -1. So these are the same. The only difference is this second has been moved from the denominator up to the numerator. Acceleration is meters per second squared, which can be written as a meter times a second to the -2. So when you move the units from the denominator to the numerator or vice versa, then the sign of the power changes. So it was a 2 here, it was divided, and since over here we're multiplying it, then it becomes a power of -2. Force is a Newton. That's a mass times acceleration, so our mass is kilograms, acceleration meters per second squared. Kilogram, meter, second to the -2. Work is force times distance. So we have force, which is our Newton, times a meter to get the units of kilogram meter squared per second to the -2. Then power is work divided by time, and that unit ends up being kilogram meter squared second to the -3. Next, we'll look at Newton's laws. Newton's first law is unbalanced forces occurring upon a mass will cause an acceleration of that mass. And the term balanced means that it's at rest or not moving. You have a reference frame and it's at rest relative to that reference frame. Or there's no acceleration taking place. Unbalanced means that an acceleration is taking place. And this becomes very important in meteorology when we're looking at parcels of air and determining whether that parcel of air is balanced, meaning whether it's staying at rest, or it's unbalanced, where that parcel is accelerating. Newton's second law is a force is proportional to the acceleration of a mass. That's the equation force is equal to mass times acceleration. And his third law is there's an equal and opposite reaction to a force. And the forces in meteorology, many of these were covered in the synoptic courses. We went over these in detail. Is the pressure gradient force, which is the flow from high to lower pressure or from higher to lower heights. The Coriolis, friction, the gravitational force, and the centrifugal. When all these forces are in balance, the air is at rest or moves at a constant velocity. When these forces, however, are not in balance, then the air is going to accelerate. So examples of that is a convective motion or an ageostrophic motion, where the pressure gradient force happens to be increasing or decreasing on a parcel of air as it's moving. And the dynamic lifting or sinking of air will also cause an acceleration. Look at gravity in a little more detail. Gravity is the attraction between masses. Value of gravity is a function of mass and the distance between those masses. And when solving equations in this course, we're going to use a constant for gravity of 9.8 meters per second squared. And the gravity is very important, obviously, as that is what keeps the atmosphere in place and prevents the atmosphere from moving off into space. Very important concept that we'll be looking at a lot in this lecture is density. Density is defined as mass divided by volume of a substance. For the standard temperature and pressure, which standard temperature and pressure is 0 degrees Celsius at 1,013.25 millibars. The density of dry air at mean sea level is approximately 1.293 kilograms per meter cubed. And on the overhead, we'll take a look at two objects that have a very different density to them. Object one here is a rock, which is fairly dense. And then we have a foam ball here, which has a much smaller density. So this foam ball is much bigger than this rock, but yet when I hold them, their masses feel like they're about the same. So the reason for that is because the atoms making up this rock are more dense, and they're also closer together than they are with the foam ball. The foam ball has a lot of air pockets in it, so it can be compressed down to a smaller volume. So solids can be compressed easily if they do have a lot of air pockets within them. Next, we'll look at air pressure. Air pressure occurs due to the mass of the air being under the influence of gravity. Pressure is force divided by the area. Force is the mass times acceleration. That's our Newton. So our force can be written as mass times acceleration, and we can call gravity an acceleration. Gravity is an acceleration that takes place. So mass times gravity is a force. And pressure is that force, that mg, divided by the area. And pressure can also be written in an equation as pressure is equal to density times gravity times height. Air pressure, more on air pressure. A metric unit of air pressure is the Pascal. That's Newton per unit area. When converting this from millibars into pascals or vice versa, it's a fairly easy conversion. 1 millibar is equal to 100 pascals, and when solving equations, it's usually the pressure is going to need to be in pascals. A millibar is also called a hectopascal. So a hectopascal and a millibar are the same unit. So 1,000 millibars is going to equal to 100,000 pascals. 1,013.25 millibars is equal to 29.92 inches of mercury. Inches of mercury is a unit that's commonly used in the United States. So that can be converted over to millibars by a conversion factor. On the overhead, we'll look at a little bit more on pressure. Pressure is force divided by area, and our units of force are mass times acceleration, where acceleration was gravity in this case. So we have mass, kilograms, times gravity, meters per second to the -2, divided by an area of meters squared. And so the basic units of a Pascal are kilogram times meter to the -1. And where this meter to the -1 came from was we had a meter squared in the denominator, and we brought this up to the numerator so that becomes a -2. So, well, you have an understood +1 with that meter, and this meter becomes a -2, so when you combine them together, that produces that -1, and then times seconds to the -2. Our pressure equation is density times gravity times height. So if we multiply the units out of each of those, density, gravity, and height, we'll come out with the pressure units. Density is kilogram per meter cubed. That's mass divided by volume. Gravity, meter times second to the -2 times height in meter. And we combine all these together, we get a kilogram meter to the -1 second to the -2. So that's one way of verifying if your equation is accurate, is to make sure that the units on both sides of the equation are the same. We need to come up with pressure units, and we do come up with units of pressure. So in our atmosphere here, we have a height here drawn of our atmosphere, an arbitrary height. Gravity is a force is pushing down. Gravitational acceleration wants to push the mass of the atmosphere down towards the surface. The air, this symbol here, is density. So the air is going to have a specific density. And then the amount of pressure that's distributed over the area. Since gravity is a constant, the pressure is going to be a function of the height. So the greater you make this depth, we can also call this thickness. The greater that height is our thickness, and the greater our pressure is going to be. It's also going to be a function of density. If the density is increased, let's say we keep the height the same, but increase the density, then that is going to increase the pressure. Since we're going to have a higher number here for density, once it's multiplied by gravity and height, you'll have a higher pressure once you have a higher density. Next, we'll look at hydrostatic balance in the atmosphere. The Earth's atmosphere stays in place due to a balance between the vertical pressure gradient force and the downward force produced by gravity. And the hydrostatic balance can be written as the change in pressure divided by the change in height is equal to the negative density times gravity, where the negative sign comes from the pressure decreasing with height. Vertical motions result when this balance is temporarily altered over a location. Now in the overhead, we're going to look at an example of finding water pressure and then look at a diagram of hydrostatic balance. So our question here is, what is the pressure of water exerted to the bottom of the 10-foot deep swimming pool? And we're going to solve the equation pressure is density times gravity times height. Gravity is a constant of 9.8 meters per second squared. Our height is in 10 feet, and as I mentioned, anytime you're given units and they're not in metric units, they need to be converted to metric units. So 10 feet is equal to 3.048 meters, and the density of water is 1,000 kilograms per meter cubed. So we're going to take these values and multiply them by each other to get our pressure. So we have 1,000 times 9.8 times 3.048 produces 29,870 for our number, and then you want to multiply the units out to make sure that they produce the unit of a Pascal, and they do. Pascal is a kilogram meter, -1 second to the -2. So our answer is 29,870 pascals, and to convert that to millibars, we divide by 100, so that's 298.7 millibars. And hydrostatic balance, so you have two competing forces here. You have a vertical pressure gradient force. The air pressure aloft is always lower than it is near the surface. So near the surface, we have about 1,000 millibars of air pressure. You go up high in the atmosphere, you have a much smaller pressure. So you always have higher pressure and lower pressure aloft in comparison to each other. And the flow is from high to low pressure, so you have a vertical pressure gradient force that wants to take the air and make it escape into space. But competing against that is the density and mass of the air and the gravity, density times gravity, which is when I want to pull that air back down towards the surface. So these two forces, one directly up, one directly down, they cancel each other out, and there is a balance in the atmosphere. So you don't get all the mass of the atmosphere squished right at the surface, and you don't get all the atmosphere escaping into space either. They balance each other out. Next, we'll go over the concept of buoyancy. In a substance with a non-homogeneous density, the substance with less density rises, and the substance with the higher density sinks. An example of this is a lava lamp. So what we're going to do now is I have a lava lamp here that I brought with me, and we're going to zoom in close on this lava lamp, and I'm going to go over some processes that are occurring in this lava lamp. The process of a lava lamp is very similar to how the atmosphere behaves in a convective type situation, where when the lava lamp is turned off and it cools, the material that's in there, that purplish material, is going to go down towards the bottom, because that purplish material is going to become more dense, it's going to cool off, and it's going to stay at the bottom. And then we turn the lava lamp on and it warms the bottom. And this is synonymous with what happens in the atmosphere. When the sun comes out during the day, the sun's energy, most of it does not get absorbed within the atmosphere, but a large portion of that solar radiation makes it all the way down to the Earth's surface and warms the Earth's surface up. So the air that's near the Earth's surface is going to be warmed up. And as it's warming up, it's going to decrease in density. It has more energy, more vibrations. It's going to expand and become less dense relative to the fluid that it's in. So in the lava lamp here, we have two different fluids here. We have the purplish fluid and we have the clear fluid. And the purplish fluid, when it warms up on the bottom from that heat source, it becomes less dense and it rises up to the top. And then once it gets to the top, it's away from its heat source, so its density is going to increase, and then it is going to sink back down to the bottom. The same process occurs in the atmosphere when daytime heating occurs. Even if you cannot see these motions occurring, since the air, you're not going to be able to see the density differences of the air, but if you could, you would see parcels of air rising and sinking back down. And if there's no cap and there's enough lifting in this situation, then a thunderstorm would be produced in the atmosphere. We'll go back and look at some more on buoyancy. The density of air is a function of the air pressure, temperature, and moisture content. Vertical movements of air will result from density differences within the air. Warmer air is less dense than the cooler air. So if you put an air that's less dense within cooler air, that less dense air is going to want to rise. If the air is more dense, then it's going to sink. So the temperature is important to buoyancy. As I mentioned, warmer air tends to have more buoyancy. Also, moisture is important. At the same temperature, air with more moisture is less dense than drier air. So the more moisture that's added there, so if you have a parcel of air near the surface and it's warm, and that's going to make it less dense. If you add more moisture to it, that's going to make it a little bit less dense also. So in a convective type situation, it helps to have that warm, moist air at the surface because it's less dense and it can rise upwards. Okay, we're back with our next experiment. And what I want to show you up here is the materials that we're going to be working with. First, I have a column of water here. This is going to represent our troposphere with water. And the other supplies I have are water balloons. I have a water warmer here that you would use to make coffee or hot chocolate or hot tea. And I have one water balloon in there that's very warm. So yes, it's a very warm balloon. And then I also have another bucket here that has ice water in there, and it has very cold water balloons in there. And the water that we have in our container here is at room temperature. So the warm water balloon is going to be much warmer. The cold water balloon is going to be much colder. And so our hypothesis is using density that the water balloon that's less dense should rise to the top, and the more dense water balloon should sink down towards the surface or the bottom. And one thing that's important to keep in mind when making these water balloons is make sure that they have no air pockets in them, because if some air gets in the water balloon, that's going to give it some upward buoyancy, and the experiment may not work. So when I made these water balloons, I tried to make sure there's only water inside the balloon. We'll start with the warm balloon, which is nice and warmed up now. And I picked the red color here to represent that it is a warm temperature. And we're going to drop that into our column of water there and watch what happens. The balloon just floats on the top there. And if we tried to push the balloon down to the surface, then it rises right back up to the top because it's less dense than the water that's in. Although there's the same substance inside the balloon, and inside and outside the balloon, it's the same substance, it's water. The density of those liquids are different. So the density of the water in the warm balloon is less dense. That causes it to rise up. And this is synonymous with a parcel of air. If this balloon started at the surface, then it would accelerate upwards to the top. So this is an unstable situation. If the balloon starts at the bottom, it's unstable. It wants to rise up since it has that positive upward buoyancy. We're going to take the warm balloon out of there now, put it back in our warmer, and then next we're going to use one of these bluish colored balloons, which has been soaking in the cold ice water. Now we should expect this balloon should go right down to the bottom, since the water in here is very cold, and so it is more dense. Now it's not frozen. If we had frozen this and it was ice, then it would actually be less dense, because water has that unusual property that it's solid. When it's ice, it'll actually float. But water has a fairly high density when it's cold and still a liquid. So we'll put our cold balloon in there now, and it goes all the way to the bottom, and it will sit there. And that's an example of a stable situation, such as the troposphere. If the air near the surface was cold, and it's colder than the surrounding environment, then it will not rise on its own. It's just going to sit there on the bottom, so it has no positive buoyancy. So the only way to get that balloon to rise is to force lift it. I'd have to put my hand in there and lift up that balloon to get it out of there. Now there's another interesting property that we can learn from this experiment, and that was gone over in the math lab, and that was thermal equilibrium. Now that cold water balloon is there at the bottom, surrounded by that warmer fluid, over time, the two temperatures are going to become in equilibrium to each other. The cold water in the balloon is going to warm up, while the warmer surrounding environment is going to cool down. Over time, they'll come to the same temperature, and once that happens, they'll have a neutral buoyancy. And when I prepared for this experiment, I wanted to see what would happen if I put a room temperature water balloon in there with the room temperature water. And it tends to have a little bit of slight positive buoyancy. It wants to rise, and probably the reason for that is it's hard to completely get all those little air pockets that get in the water balloon. And also the balloon membrane is a little bit less dense than the water. So if we keep this here, over time, maybe by the end of the lecture, it'll have come into a thermal equilibrium, and then that blue balloon will actually rise back up. The last topic that we're going to look at today is pressure systems and the vertical structure of those pressure systems in the atmosphere. We'll look at cold core lows, thermal lows, tropical cyclones, cold core lows, and warm core highs. We'll start with a cold core low. With a cold core low, there's rising air in all levels of the troposphere. A cold core low tilts with height, especially in its developing stages. The coldest temperatures are at the center of the low, since it has its lowest heights aloft near the center. And air is cooled in this type of low by adiabatic expansion, and also evaporation from precipitation also cools the air. Some other characteristics is that they are deep cored, which means they extend throughout the atmosphere. Developed cold cores lows will show at each mandatory level. They'll have closed height contours and low levels, and shows a synoptic scale trough in the upper level. So when a cold air mass invades the United States in the low levels, you'll often notice that there's a trough aloft above that. Initially developed due to jet streaks in synoptic thermal gradient zones or vorticity spin-up. On the overhead, we'll take a look at an example of a cold core low. Here is our surface, and this is the position of our low pressure at the surface. And as is mentioned, it tends to tilt with height, since you'll have cold air on one side. This is north, and this is south. So we have the cold air towards the north. This would be behind the cold front to the north of the low. And you'll tend to have lower heights above that colder air. You also have rising air with the cold core low, and that helps cool the air even further. And if precipitation occurs, that's going to cool the air also. So this is a cross-sectional view, and you'll notice how the 700, 500, 300 millibar pressure surfaces dip down closer to the surface, because when the air is colder, the air is more dense. And the more dense, more compacted air will cause the pressure systems to be closer together. Next, we'll look at the thermal low. Thermal lows are shallow and most intense at the surface. They develop due to strong surface heating. Hot air due to intense thermal buildup results in positive buoyancy at the surface. The middle and upper levels tend to be stable in a thermal low situation. They're most common in the southwestern United States in summer. They develop over land, especially land that is dry with little vegetation. Due to the dryness of the planetary boundary layer, precipitation is usually not common, but in some situations, if enough moisture works into the system, there can be an isolated afternoon thunderstorm. We'll take a look at an example of what the thermal low looks like. We have at the surface our hot air, and this air is hot and it rises. And in the rising motion, this intense rising motion you get from this positive buoyancy, causes the pressure to decrease. So the pressure is decreasing because the air is rising, and it's also cooling off very quickly. Since this air is dry, it's cooling off at the dry adiabatic collapse rate as it's rising. But it usually doesn't rise up very far into the troposphere before it encounters a stable layer. So you'll often, in the southwestern part of the United States, you'll see a low pressure system there, but not much weather occurring with it. Next, we'll look at the tropical cyclone. It's deeper than the thermal low, although they do weaken with height in the upper levels. Subsidence in the center causes compression and warming. Air rises rapidly around the edges of the eye. An enormous amount of latent heat is released, because unlike The thermal low, the tropical cyclone, has an enormous amount of moisture, so its rising motion releases an enormous amount of latent heat, and that continues to give the parcels positive buoyancy. Unlike the thermal low, which develops over land, the tropical cyclone develops over the water. The warm core low is strongest when vertically stacked, so significant wind shear will weaken a warm core low. So if you have a tropical system or a hurricane, it helps to have weaker winds aloft for it to develop. And on the overhead, we'll take a look at a tropical cyclone. We have an intense low pressure at the surface that draws in air at the surface very rapidly, strong pressure gradient force. And then in the eye wall, you have intense convective motions. And then in the center, though, you have where the air is actually sinking and warming by compression, but you still have a very low pressure since a lot of the mass has been evacuated away. And then in the upper levels, you'll actually see indications that look more like a high pressure system, where you have the air moving away from the tropical system. So the air is drawn in at the surface and rises rapidly. And then for the system to be intense, it helps to have a weak upper level wind. So if you have a high pressure aloft from the hurricane or tropical system, that generally help it develop further. Next, we'll look at cold core highs. Cold core high, high pressure at the surface due to cold, dense air, but with troughing in the upper troposphere since they tend to be shallow. Precipitation is generally lacking near the cold core high center. It usually has fairly low dew points and cold air. They cover a large spatial area, and they develop over high latitudinal land. So a polar high pressure system would be an example of a cold core high. And we'll take a look at that on the overhead. We're in a cold core high. You'll have a very cold air that invades the lower troposphere. Especially as the cold air moves south, it tends to get shallower and shallower. That cold, dense air wants to stay near the surface. So you have your coldest, densest air near the surface, so you get a high pressure. Because of how dense that air is, it produces a higher